Wood with Citadel Civil Engineering. This is CIVL202 Statics, and in this lecture we're going to continue to discuss moments in force systems, in non-concurrent force systems, but now we're going to begin thinking about them in 3D, so this can get a little complicated. Again, I want to remind you that statics is the first of our dialectic stage, so we're using these ideas of lever arms and rotation and moments that we learned about in physics. We're using cross products today that we've hopefully learned about in our math classes. And we're going to be using these concepts going forward. So it's worth mastering these concepts. We'll use a similar cross product concept in dynamics and in mechanics and materials and structural analysis. You'll be calculating moments all the time in your analysis going forward. This is a force system, so you can see we're moved over into that rigid body column because we're now going to be able to model objects with length, and that's going to be very useful to us, but that length causes a tendency to rotation, and because in statics nothing moves, we're going to want to be able to resist that rotation. And so with this in mind, let's look at a picture from our textbook that attempts to represent in 2D a 3D rotation. So we have a position vector, in this case that R vector here, that we're looking at right here, that R vector. That R vector in this case has a positive X, Y, and Z component. And then we're doing a cross product where we're multiplying it by the force that's being applied at out of this location. You can see very lightly shaded, hopefully, that there's a little triangle here that indicates the RF plane. And then perpendicular to that, we have the moment, which is drawn in the direction of the axis it's rotating about. So an easy way to kind of help you picture what that's doing is we have a screwdriver. We rotate screwdrivers, right? We apply a moment to the end. Well, the moment's along the screwdriver. It's really about the axis of the screwdriver as we twist it. But that's kind of a good way to model the axis. Think about the axis that it's pointed along. And so we can see that curlicue twist there. Now, this is really complicated. I don't really know what it means. So we can look at another picture from our book, and it breaks those forces into their Cartesian components and the position vector into the Cartesian component. And now we can start thinking about, well, what does each component of that force contribute to the tendency to cause rotation about each of the axes? If we look at that axis for the moment, it has three components. So we're going to see some rotation about the x-axis, some rotation about the y-axis, and some rotation about the z-axis, all generated by this generic force acting at some arbitrary distance. And so let's see if we can break that down. The first place that we'd want to start is by talking about our moment about the x-axis. So if we look at our picture over here, we have our x-axis here, and we're going to think about what of those moments, or which of the forces would cause rotation about that x-axis, the one coming out of the board, and we need to identify the perpendicular distances to the force. So remember, we defined a moment as the perpendicular distance times the total force. That's a great way to do the mental model this time around. And so we're going to try to identify those things that would cause rotation about the x-axis, and then use our right-hand rule to figure out if our thumb points in the positive x direction or in the negative x direction to figure out the sign. So we're looking for both the magnitude and the direction pieces. So the first component we might look at is our force in the x direction right here. And we'll notice that our force in the x direction and our x-axis, oddly enough, point in the same direction. And so our x component of the force, Fx, is parallel. Hopefully you know this notation. I've drawn two lines parallel to one another. It's parallel to the x-axis. And so we're going to ask ourselves, would that ever cause rotation about the x-axis? If they're pointed in the same direction, it's just going to pull along the x-axis, which means there's actually no perpendicular distance that would cause rotation. So the net result of this is that our perpendicular distance, we use R perpendicular, is going to be equal to 0. No moment there. So let's think about our y direction, Fy, the force y, and what its perpendicular distance is. So force y here is pointed this direction. If we're going back to the x-axis, we can extend our line of action along the line to point E, and we want to find the perpendicular distance. So it's from the x-axis, which in this case is going to be this distance here, which is actually RZ. So it's perpendicular by the distance RZ. Maybe we call that just Z, but I think this works for us, RZ. And then we have to think about our right-hand rule, whether this is positive or negative. All right, let's think about how we would do the sign for this. I've sketched out a little XYZ coordinate system to help me have something to run my hands along. In this case, my R component, we're talking about the RZ component, RZ, that points up. My FY component points to the left in the Y direction, and then my thumb ends up pointing into the board. Y'all see that? Or I could do R cross F into the board is negative. X is supposed to come out of the board, so in this case, if it's into the board, I'm going to get a negative moment. So my right-hand rule tells me that this is negative. Okay. Let's think about force Z now. Okay, so we've looked at force X, force Y, and now we're looking at force Z. We're looking for its perpendicular distance from the x-axis, so we're going to extend its line of action down to D, and this is the perpendicular distance that would take us back to the x-axis, which is RY. So force Z is perpendicular by the distance RY, which means that what's our right-hand rule? Let's look at that. Okay, so we need RZ, RY, R cross F, so RY to the right, and then force Z is up, and then my thumb comes out of the board with my right-hand rule. Or I can do R cross F, thumb out of the board, and it's causing positive rotation about the x-axis, like so. And now that we have my forces and their perpendicular distances with their signs, I can actually articulate that my moment about the x-axis is going to be equal to Ry times Fz, Ry times Fz minus Rz times Fy. And the reason I can just add these up is because they all point about the x-axis or in the I direction. Okay, so far so good. I've calculated my moment, that tendency to cause rotation, about the x-axis. All right, let's think about the same thing for our y-axis. So we'll start with force x, and we'll figure out the distance to the y-axis. So if we look at our diagram again, here's my force x, here's my y-axis. If I take my force x, I extend it back, the perpendicular distance back to the y-axis is this guy right here, which is Rz. So it's perpendicular by the distance Rz. Now, if I want to think about my right-hand rule, I'm going to do R cross F. So my R is in the Z direction, my F is in the X direction, and then my thumb points in the positive Y direction, or RZ cross FX gives me that positive Y direction. So my right-hand rule tells me that my rotation is positive. Hopefully that makes sense. Keep in mind, part of the reason that you're taking the class and not just watching YouTube videos to learn statics is that if you have questions, come ready to ask them in class. We'll work example problems together, and I want to make sure that you get comfortable with this concept. All right, so we got that going for us. Let's look at force Y. Force Y. Okay, well, force Y is here. It points in the same direction as the y-axis, so they're both pulling in the y-axis direction. And so when we think about it pulling in the y-axis direction, it would cause translation, but it's not going to cause any rotation because it's parallel to one another. So our perpendicular distance is going to be equal to 0, like so. Okay, let's look at force Z and what its perpendicular distance is. Here's my force Z. I extend the line of action down. My perpendicular distance is dB. Well, that's the same as Rx. So my perpendicular distance is going to be equal to Rx. Let's think about my right-hand rule. My R is in the X direction. My Y is in the Z direction. And that means my thumb points in the negative Y direction. So sorry, let me say that again. My position vector R is in the X direction. My force is in the Z direction. And my thumb points in the negative Y direction. Or I could do R cross F and get that negative Y direction. Both of those would work there. And so my right-hand rule tells me that this is going to be negative. So if I want to look at the overall moment about the y-axis, I would have RZ times Fx minus Rx times Fz, and I can just add them up like this because they're all about the y-axis, which I can indicate with the J unit vector. Are y'all starting to see a pattern here? I hope you're starting to see a pattern. Let's do one more about the z-axis. So Fx, let's figure out what its perpendicular distance is. I bet you can tell already just by the pattern. So here's my force x. My z-axis is what I'm looking for back here. So my line of action extends back. This is my perpendicular distance from the z-axis, which means that my perpendicular distance is ry. So it's perpendicular by the distance ry. If I use my right-hand rule, ry cross x goes down. Okay, instead of popping my shoulder out of socket, r cross f gives me a negative z direction, or r cross f negative z. So my right-hand rule tells me that this moment is going to be negative about the z-axis. Fy is perpendicular by some distance. Let's look at that on our picture. Here's our force Fy. We extend the line of action back. We're looking for the perpendicular distance to the z-axis, which tells us that this distance is Rx. Use my right-hand rule. So Rx cross Fy gives me the positive z direction, or R cross F, positive z direction like so, which means that my right-hand rule is positive. And then finally, if I think about the force z, it's going to be parallel to the z-axis because my perpendicular distance will be 0. All right, so we've done that. Finally, we can add up our terms here. And we would say moment about the z-axis is going to be equal to Rx times Fy minus Ry times Fx, and it's all pointed in the k direction. All the rotation about the moment there. Now, you survived that. Maybe it made sense, maybe it didn't. Here's the thing about it. We can use our right-hand rule just the way we did to identify all these different components and to break it down and to derive it every time. Alternatively, we can go straight to your FE reference handbook, which actually has these different components identified as the moment. That sounds easier, especially if you're allowed to have your FE reference handbook, which you will be, both in this class and on the FE exam. That's fine. And in 2D, really, this isn't bad at all because we know that in 2D, our forces are only in the X and Y direction. So the FZ component goes to 0, and the RZ component goes to 0. So this goes to 0, and this goes to 0. So we only have our K component. So often we'll use our right-hand rule and our scalar notation to calculate moment in 2D. But in 3D, it's a lot nastier. So sometimes we do it this way, pulling data directly from our FE reference handbook, looking at moments or couples. Now, the other way that we can do this is we can remember our mathematics of a vector cross product. And I really like this method because I'm really good at memorizing procedures or remembering procedures. I'm less good at memorizing equations. So when I think about the procedure, we have to remind ourselves that the moment, the total moment about any point is equal to R cross F. And I know some of you look at this and go, I learned that in calculus, in Cal 3. I know how to do this cross product. And so maybe you've got a couple of different ways you could do the cross product. Maybe you duplicate columns and you work diagonals. I'm going to show you the version that's in our textbook. However you want to do that, you're welcome to do this. But when we solve a cross product like this, what we're going to do is we're going to create a determinant of a matrix. And so when we're doing a cross product to calculate a moment, our first row is our unit vectors, I, J, and K. Again, I'm doing this as another way to calculate exactly the same thing. The second row is going to be my first vector. So this will be Rx and Ry and RZ. And then my last row will be the last vector. So Fx, Fy, and Fz. Order does matter. If we flip the order, we get all of the signs wrong, 100% of the signs wrong. And if you flip the order, you lose some points on the next exam, which I don't want for you. So we've got this determinant matrix. Now we have to solve out this determinant matrix. The method that I like to use evaluates each column, a submatrix, for each one by itself. So if I'm looking at the I column, I'm going to cover up the I column. And then I'm going to determine the determinant of this little 2 by 2. And so I'm going to do Ry times Fz. When I move up, it becomes negative Rz times Fy. Again, hopefully this is something you learned in a math class. Maybe you learned a different method. That's fine. And we get something like this. And I'll go ahead and color code it. That gives me my I component. Hey, wait a second. That's moment about the x-axis. Have I written this somewhere else on the board? Look at that. Here, let me even blow it up so you can see it even better. RYFZ minus RZFY. Whoo. Okay, remember when we're thinking about our models, we have reality. It's complicated. We have our mental model, our understanding. We built this out of our mental model, and then we have our engineering and math model. Turns out we don't lose anything in this case by just trusting the mathematics. It's fantastic. I like it a lot. All right, so we go there. Let's look at our J column. One of the things we have to remember when we're using this particular method, it's just a function of how this method works, is that we have to introduce this negative term in front of the J. Okay, don't forget that if you're using this particular method. I cover up my J column, and then I do the 2 by 2 determinant where I'm going to say Rx times Fz minus Rz times Fx. So Rx times Fz minus Rz times Fx. And we'll notice here that it's actually the same as this once I multiply that negative sign through. So this negative sign is a real big deal. Got to make sure we have that negative sign in there. Follow the process. And then finally, I can do the K term like so. I'm just going to add the K term on. So the moment about the K axis, K is going to be Rx times Fy minus Ry times Fx. And we get the same answer. So there's our moment there. Rather than doing the complicated mental model, perpendicular distance times force, totally fine. Have fun doing that for the scalar method. And in fact, we'll often do that when we're only looking at the 2D component. We can do a vector cross product where we just remember this. Or, because we're engineers and we're usually going to have references available, we can go to our FE reference handbook and find this equation in this form straight out of the FE reference handbook, getting the same answer. All right, this has been Moments. We'll work a problem or two together in class. We'll get our hands on it. Come ready to ask questions. I know this is confusing. I know it's difficult when we think about the right-hand rule, and so we'll work on that right-hand rule together more in class, and I'll see you then.